talk about the capacitor. Ooh. All right. Full disclosure. Don't touch a capacitor. If you don't know if it has voltage, or if you don't know it's live, even if the circuit is live, it could still kill you. I will, you know what, I'll do a demonstration video this week sometime of me discharging a capacitor and not blowing myself up. That'll be fun. I told you this was going to be an easy week. This one's only got 8 slides, and the end of it's going to be a lab. So, capacitors, what are they? Very similar to batteries. Very similar. Essentially, their jobs are identical. They do the same thing. Their whole purpose is to store energy, but they have different applications, different purposes. Where batteries store chemical energy, right? Or, well, we're going to stick with chemical energy. Uh, to convert for electrical energy due to the bias between the plates, capacitors store energy in their fields, very similar to a magnet, but temporary. They're found in, I say almost every electrical device. At this point, I can say every electrical device. And here's some differentiating factors. Capacitors can store so much faster than a batteries. They can build up charge so much faster, and they can discharge so much faster. But their storage potential per capita, pound per pound, batteries have it beat. The chemical capacitance, the voltage capacitance for a chemical battery is always going to far exceed that of the energy capacitance for a capacitor. So in closing, capacitors can store much less voltage, batteries can store much more voltage, but capacitors can do quick, very swift discharges and charge ups, whereas batteries are much slower due to the chemical nature. We got a new symbol, which is always exciting, and a unit of measure, the farad. If you see this symbol, you're looking at American capacitors. If you see curved on one side, that's how the Europeans show their capacitors. Sometimes you'll see a line in between, and we'll have some unique edge cases for capacitors that we'll look at later on. But for purposes of right now and the labs, the assignments, this will be the symbol that you see. I don't know why this isn't in there, but capacitors actually have a polarity. There is a positive side and a negative side. If you see a stripe, which you will almost always see a stripe or a line on a capacitor, that is the negative side. You want electrons entering that side, not positive charge carriers from the conventional energy transfer to go on that side. So just think the stripe side is negative. All right. So as we were talking about, the capacitor storage potential is known as capacitance. It's measured in farads after Michael Faraday, American inventor, super cool guy. Here's a picture of him. It's always good when we get to see inventors and great engineers because they're so recent. Gives you an idea of how we've been playing with batteries since Volta's time. Actually, before that, if you want to talk about the Babylon battery and the Mecca battery and all those fun representations of being able to store kinetic difference in voltage via chemical process. And then we got this guy, circa a long time ago, but obviously not so long ago that we didn't have pictures. A 1 farad capacitor, which is, by the way, an absolutely huge amount, because we usually look at farads in the micro scale, can store 1 coulomb of charge. That's this many billion electrons at 1 volt. If a capacitor can store that, it would be the size of a 2-liter bottle. We're playing with something far more modest. We'll almost always see this micro terminology, lowercase u, before the measuring indicator, before the farad symbol. if you're playing around with a capacitor that's in the farads, not in the micro, even if it's in the centi, I don't know, stay away from that thing. That's way more electricity. That's industrial purposes. Don't play with that at all. All right, so let's talk about how they work. Any questions on any of that so far? Oh, good. I want to hurry up and burn through this because I want you guys to get to a lab. Okay, so capacitors, oh, I did say this. They have two terminals. There is a positive, negative side, and the negative side is denoted with what's on the outer? What's on the outer side? Somebody tell me. It's going to be a stripe. It's going to be a line. It's going to be something other than the rest of the sheathing, which is usually a ceramic or a polyurethane coating around capacitors. So they have a positive and negative side. The terminals connect to conductive plates, but there's a semiconductor or an insulator in here. The plates don't ever touch. That's key because if not, it would just be almost a quasi-resistor. And it allows them to hold opposing charges on either side. Now, what this actually is producing is very similar to a battery. We have a bias. We have electrons on one side, we have positive charge carriers on the other side, and the bigger the difference between these two voltages creates a, or whoops, the bigger the difference between the charge carrier and the electrons, that bias, is the voltage level. But instead of being held within plates or a chemically reactive substance, it's stored in an electrical field. Sometimes you'll see it's called a dielectric material, mica, Teflon, mylar, sometimes even air or like they call it doped air, air that has like extra helium molecules in it. Dielectric means the the material will polarize. It'll allow one-way transmission of electrons if there's an electric field present. So we're doing the same thing we're doing with the battery, but instead of using chemicals, we're using that electrical field, similar to what you see with a magnet. So because these are stored within a field, fields quickly get up to full power and they quickly collapse, which means they push energy out much faster than a battery. So much more practical applications for fast switching. That potential difference that we were talking about, the voltage, the opposite sides, one has positive charge carriers. Oops. When it's attached to a battery, the electron flows into the capacitor. Electrons gather on one side. Charge carriers can't be connected between the two, and essentially everything in between, that difference between electrons and charge carriers on either side, represent energy in the form of an electrical field. The charge carriers inside become highly polarized, which means one side has a lot of positive charge carriers, the other side has a lot of electrons, and the difference between the two is a voltage. If you were to measure it with a multimeter or a voltmeter, you would see a very similar reading to what you would do if you were looking at a battery. So this is an analogy that I like to use when we're talking about a capacitor. A capacitor could be considered like a water tower. If there was a water source and you filled up this water tower and then all of a sudden the water source got cut off or it was inconsistent, if you were downrange, you would still see the water flowing because the water fills up in this tower and it's essentially gives you a little bit of a buffer between any inconsistencies or any breakage from the power source itself. And that's pretty much how we use them. We use them to smooth over voltages. We use them to make electricity a little more consistent. Because if we have power going through a pipe and it's just a straight through pipe, something happens to the source, then whatever was trying to get energy on the other side would be starved of energy. We throw a capacitor in between the two, and this slowly, I should say slowly, it quickly fills up, and then something happens to the power source down the chain. Whatever's on the other end isn't getting starved of a power source because the capacitor is going to let out what it's stored up um, through the rest of the system. Does this illustration make a little more sense than trying to show blue and green or green and orange dots at a rectangle? I think there may
Yes.
actually. Oh, sorry. Go ahead.
It's very helpful.
Cool. Excellent. There may actually be an answer, or a question on the quiz that asks what kind of analogy can you make to a capacitor? Um, yeah, a water tower would be a good one. So it's a lot easier to show it than it is to describe it. It's lab time. Let's do this. Do you guys have your simulators ready?
Yep.
Yep.
Oh,
Yes.
excellent. Okay, so we're going to be messing with a few components here. We're going to be using a DC voltage source, even though we were just learning about AC. I want you to make note of the polarity here. We're going to be using a switch to be able to cut on and off the power. We're going to use two resistors to try to limit the flow so we can get the most out of this capacitor. And here we have a 100 microfarad capacitor in the center. And then there's a load. It's a simple LED or a bulb. I want you guys to take some time because it's 4:50. We only got a couple minutes left. I want you guys to reconstruct this as best you can. And then somebody, whoever's first one done, I want you to share your screen. Let's see what you got.